Good morning, everyone. Welcome to today's topic of our 2026 Crops Winter webinar series. Today, our topic is on impacts of tillage operations on soil properties. My name is Javjot Singh Sandhu, and I'm an intern extension agrologist with the Saskatchewan Ministry of Agriculture in the North Balfour Regional Office. I will be sharing this morning event. CEUs are being offered for CCAs on this webinar. In order to get credit, you must attend the entire live event. There will be a QR code at the end of the presentation to collect credit. If you missed the code and have attended live, please email us afterward and we can work with you to get your credit. Before we start with the formal presentation, I have a few items to share. Our crop extension specialists put on this webinar series each year. We work out of 10 different offices across the province. Each office contains a wide variety of specialists that can help you with any agriculture-based question. To connect with our specialist, please call your local regional office or the Ag Knowledge Center at the number provided. There are 8 agri-arm sites located throughout the province that are dedicated to bringing the industry Saskatchewan-specific information and demonstration on new and existing agriculture practices. If you are interested in learning more, please follow the QR code on the screen. If you ever heard the word on the radio, Saskatchewan is 98% completed the harvest this week, then you have likely heard of the crop report. My colleagues in the Moisture office write the crop report each week during the growing season based on the data collected from crop reporter across the province. I would like to thank all our current crop reporter for helping us achieve this comprehensive report. I would like to invite any new crop reporter to sign up. Please use QR code to sign up today. I also wanted to mention that the 2026 Crop Diagnosis School will be at Swift Current this year on July 29 and 30th. More details are coming soon on that event, along with some other upcoming field days hosted by local agri-arm research site. Please note our upcoming schedule of winter crops webinar, but another webinar series you may be interested in is brought to you by the Rangeland Management Specialist and Agri-Environment Specialist is the Weed Management webinar series registered today on our website at the Sask Ag event calendar. Lastly, we want to make sure everyone is aware of the funding available through the Sustainable Canadian Agriculture Partnership. You can reach out to your local agriculture program specialist to find out what funding you may qualify for. Along with this information, we have additional resources for everyone under our handout section in the chat box area of the toolbar. These will be shared along with the recording after the webinar is completed. Today's presentation will be followed by Q&A with Jeff Schoenau. The main hub for today will be your webinar screen, and as mentioned, we will share the relevant downloadable handouts with you in the chat box area. The entire session will be recorded, so if you miss anything or wish to revisit any of the presentation, you will be able to. Recording link will be sent out later this week in a follow-up email. An evaluation will pop up at the end of the webinar this morning. Please ensure that you fill out the evaluation, as these help us determine what topics you want to learn more about and help us prioritize research need for future. We have a few housekeeping notes to keep in mind during the webinar. If anybody has any question during any of the presentation, you may type them in the question box in the top right-hand side of the control panel. We will try to get to as many of your questions as possible. Your question will remain anonymous and will only be sent to me during the presentation. You will be muted so that we can ensure there's no feedback that will interfere with the audio. Now let's get started. Dr. Jeff Schoenau is a professor of soil fertility and professional agrologist who works in the Department of Soil Science at the University of Saskatchewan. He holds the Saskatchewan Ministry of Agriculture Soil and Nutrient Management Chair in the College of Agriculture and Bioresources. He was born in Saskatchewan, completed his undergrad and grad degree in 1980s in the College of Agriculture at the University of Saskatchewan, has worked there since. His research, teaching, and extension activities deal with soil fertility and fertilizer and nutrient cycling and soil management practices in the prairie cropping system. He also farms with his spouse near Central Butte, Saskatchewan. We will start whenever you are ready, Jeff.
Great. Thanks a lot. And it's great to be here this morning with all you folks to talk a little bit about impacts of tillage on soil properties and crop yield. In the next 45 minutes or so, what I'm going to do is give a little bit of an overview of what tillage does in terms of its effects on the soil, and then give some examples and draw on that on its effects using some research work that we have done in the past over the years on the effects of different tillage practices on soil conditions and crop yields. So I guess first we go all the way to the basics, folks. What are soils made of? And soils, of course, are made of mineral materials, organic matter, and pores. Pores are the what are called the holes or the voids in the soil. And we have different kinds of pores in the soil. We have the macropores, which are the big pores, which at field capacity, kind of optimal moisture content, those big pores are drained and allow the exchange of air with roots and microorganisms in the soil. They're well aerated. We also have what are called the micropores, and the micropores are the small pores there, and at field capacity and even at moisture contents below field capacity, those micropores often are filled with water. They're often contained within aggregates or conglomerates within the soil, and because of that high water content, often they're anaerobic as well. So we've got this structure of the soil, the mineral material, and the pores in between, and collectively what that gives rise to is a density of the soil, what we call a bulk density, that includes the density of the mineral materials and the organic materials, and also the density, or we actually don't have any density, but also that space that's occupied by the pores. I'm going to come back to that a little bit later on because it is important, but thinking about then what is tillage, what we're going to talk about and what we think about when it comes to tillage is really disturbing that soil, folks, through various mechanical means. And the kind of disturbance that you might experience from that, of course, depends on the implement that's being used. And that might be something like a harrow with tines on it that creates relatively little mixing and typically confined to a shallow depth within 3 or 4 centimeters of the surface. The intensity of that depends on the angle of the harrow tines and the travel speed. Then we move down the list there, something maybe that's a little bit more intensive, which would be a chisel plow, which may or may not be followed by harrows behind it. And those sweeps on there create a kind of lifting action, as well as the edges, of course, being very effective in killing weeds. We move on to something like a disc, which is a little bit more aggressive. It does create more of a chopping, a mixing, and more burial of the residue. And then finally there we have a vertical tillage operations equipment, and there's many different variations of these, which typically do a fair bit of chopping, of soil disturbance, moving the soil around, and leaving that soil in many cases with not a lot of residue cover on the surface, and a level fairly packed layer there behind that can be seeded into quite effectively, especially if you've got a lot of residue that you need to deal with and need to reduce. So what does tillage do? One of the things that it does is it reduces that bulk density. It increases the porosity, the pore spaces, and we have more pore spaces there. That certainly can promote aeration, can promote water infiltration or water entry. The other thing that tillage does, I think we're well aware of, is it does dry out that surface soil, and that may be desirable in some cases when we have a really wet soil and we want to be able to get into that field earlier on. It also seals up the cracks. And by sealing up those cracks and creating a kind of a dust mulch on the surface, it can actually help preserve moisture down deeper by reducing the evaporative losses from the soil. Recognizing, of course, dust mulch, which was used in the 1930s, led to a lot of issues with wind erosion. That dry surface soil certainly can impede germination, especially of shallow-seeded crops. The other thing that tillage does, it incorporates that residue, accelerates its decomposition. It also breaks down aggregates, larger aggregates into smaller aggregates. It exposes the organic matter inside, and overall tends to accelerate organic matter decomposition, increase that microbial activity, and the ability of the microorganisms to access those organic materials and carry out decomposition. Of course, the other thing that tillage does, it kills weeds. We also recognize that it can promote germination of some weeds, and sometimes actually a tillage operation in early spring may be used to promote the germination of weed seeds that can then be dealt with later on in a single application of a herbicide. Promotion of germination, I think, of weeds like a kochia weed, for example. So yeah, tillage affects a lot of different aspects of soil properties and functioning. So why would we till? I guess what maybe first comes to mind, and particularly in my own experience as a farmer, as a grower, you may have these areas within a field that because they become ephemerally flooded or flooded at one time, that the weeds started to grow in there, and finally, when you maybe came along with a couple of dry years afterwards, that area dried out. For a couple of years, you couldn't seed it before. You got a lot of weeds in there. To get in there and really get rid of those weeds and prepare that area to be brought into crop production. Really, as well, anytime you've got a lot of residue out there in that field where there's going to be interference with your seeding equipment, tillage may be warranted. Mechanical control of weed population. I think it's always said there's no weeds out there that are resistant to steel. So that's another potential application where you would look at tillage. And finally, there may be some soil structural issues, such as compacted zones in heavy traffic areas within a field, where some type of a tillage would be warranted to loosen that soil up and reduce the strength and improve the infiltration. And I'm going to talk about that a little bit later on in the presentation as well. So the first thing I want to cover is some work that we did quite a long while ago, actually pretty close to 20 years ago, addressing the question, what happens when you till a no-till soil with one cycle of shallow tillage? And this was work that was done by a graduate student, Chris Ban, who worked with myself and Mike Grievers as a master's project. And if anybody's interested in the details of this, Chris has got his master's thesis and as well as published as a paper in the Canadian Journal of Soil Science. But in this particular study, and I mean, in the mid-2000s, we talk about long-term no-till. These were fields that we worked with at 3 different locations that had been in no-till for about 15 years. And I guess if you did this again, which would be very interesting, you'd be able to look at these impacts after 30 years of no-till. But we had 3 sites. One in the brown soil zone at Central Butte, it was a site on my farm. Another one in the black at Rosthern. And then finally one in the gray-black over here in the Tisdale area. And so the tillage operations that we were looking at, and I'll explain those in just a moment, involved a chisel plow and a tandem disc. And what we had in this study were 4 tillage treatments that are identified, and in the upcoming figures and tables, you'll be able to see these abbreviations. No-till, which was really a no preceding tillage, no-till, kind of business as usual. A minimum till, where there was a single tillage operation prior to seeding that was done in the spring using a chisel plow, 30 centimeter sweeps, 30 centimeter row spacing at a depth of 7 to 8 centimeters and traveling at about 6.4 kilometers per hour, about 4 or 5 miles an hour. And another treatment we had was what we called conventional tillage, which was really 2 operations with the chisel plow, both a spring and a preceding fall tillage operation. And finally, what we had was what was called the maximum tillage treatment that included a fall till and a spring till, and then an additional go over with the tandem disc prior to seeding. It was a tandem disc notch blades traveling at 6.4 kilometers an hour. So these tillage treatments carried out in the fall of 2004 and the spring of 2005. And then what we did, we went in afterwards and we looked at the impact on various soil properties. And I'll start out first with the surface soil organic carbon content. And this is the mass of carbon in different depths at the surface. We got 0 to 5 centimeters, 5 to 10 centimeters, and then the total mass in the top 10 centimeters. And when we look at this at our three sites, Central Butte, Rosthern, and Tisdale, statistically, and this was at the 10% probability level, so we were working at a fairly generous level in terms of whether we called it significant or not. We really didn't see any significant, statistically significant effect on the total soil organic carbon amount in that top 10 centimeters from that one cycle of tillage. But you can see there is a trend at all of the sites for the mass of that carbon to be slightly lower and increasing as the intensity, and decreasing as the intensity of the tillage increases. I think it is important to recognize that you really wouldn't expect to be able to measure a change in something in a pool of carbon in the soil as big as the total amount of organic carbon in the soil over just 1 year of a management practice. But nonetheless, we do see a bit of a trend there, and part of that trend may also be because the density of the soil has been reduced by the tillage. So I guess if we were to do this again, it would be I think more representative or realistic to look at this on an equivalent mass basis. But nonetheless, there is a trend there, but not statistically significant, and that really didn't surprise us. Some of the other more dynamic properties that we looked at really did show more of an effect of the tillage operation. And one of the things that we looked at was the soil extractable nitrate. And the nitrate, following those different tillage operations in the spring after the last one was completed, at the Central Butte site, looking at the nitrate in the different depths, not a big effect, but maybe actually overall a little bit of an effect of actually increasing the nitrate content as a result of tillage, maybe reflecting increased mineralization because of breakdown of those aggregates. There was not a lot of straw at the Central Butte site. And actually, when we did this, it was after a chem fallow period. And so there was just standing straw. So not a lot of potential for microbial immobilization. But you will note here, and especially what we see here in the Rosthern site, and especially in the Tisdale site, as we increase the intensity of the tillage, especially in those maximum till where we went spring and fall with a chisel plow plus a tandem disc in the spring, we do see a significant reduction in the soil nitrate content following. And really what we're seeing there is that those two sites, especially the Tisdale site, there was a lot of wheat straw. And that fresh wheat straw with a high carbon to nitrogen ratio, when it's worked in, temporarily ties up that available nitrogen. We also looked at soil extractable phosphorus in this study. And what we see here, first off, when we look at this extractable available phosphorus here, distribution with different depths in the soil profile at the sites, we see that typical stratification of the phosphorus with the highest concentrations of available phosphorus there close to the surface and decreasing. And what was the impact of the tillage on that stratification? Well, we can see there with our tillage there, overall, looking at one depth and the effect of the tillage operation, there was really no significant effect on the concentration. But overall, as we look at the distribution of phosphorus across those three depths, we can see it kind of smoothing out where the concentration in the surface is decreasing and the concentration deeper down tends to be increasing. Really seeing this at all of the sites. So the tillage, and especially when we look at that maximum till, tended to reduce that stratification of the phosphorus close to the surface because of that mixing, homogenization. But when we looked at the phosphorus uptake, we really couldn't find any significant effect on that. Now, maybe if we fast forwarded with another 15 years of no-till on that and more stratification, maybe we might see more of an impact. But in this particular case, we didn't. The bulk density. What was the influence of the tillage on the bulk density? No surprises there. The tillage reduced the bulk density, and that seemed to be particularly the case in this 5 to 10 centimeter depth, which tended to be a little bit higher in bulk density overall across the sites, especially at the Central Butte and Rosthern site. And it did reduce the bulk density, especially at that 5 to 10 centimeter depth, which was about the depth at which we were working with, where the actual tillage implement was in the soil, if it was the chisel plow doing its job of lifting up that soil. We also looked at soil pH, and overall, you can see here at these 3 sites, we really weren't dealing with a particularly low pH close to neutrality. The distribution of the pH was pretty uniform with depth, but particularly in that 5 to 10 centimeter depth layer, though, you will note that was at all 3 sites where we tended to have the lowest pH. And that's about maybe the depth where the nitrogen fertilizer was being placed. Again, would be interesting to look at that right now and see how that trend maybe has progressed. But what we see here is with the tillage operation, we do see some homogenization of that pH, and that pH coming up in that 5 to 10 centimeter layer with the tillage coming up slightly, not a big effect, but there is a trend towards that tillage then smoothing out that pH, those differences that we see among of the different depths, and bringing that pH up a little bit in that 5 to 10 centimeter layer. So yeah, tillage can help to smooth out or homogenize the pH, and especially if you've got a B horizon or a BMK that's got a little bit of carbonates, a calcium carbonate closer to that surface, mixing that in with the soil further closer to the surface, I think would maybe produce a more substantial increase in pH at that depth where you're placing your nitrogen fertilizer. Aggregate mean weight diameter, or the size of the aggregates, really no significant effect, folks. But at Central Butte site, there was a trend. There was a lot of variability in this data, but we did tend to see, especially that low organic matter site, not a lot of straw. That tillage was tending to be bringing up bigger chunks or lumps, as you would say, of soil there, but still not statistically significant. Temperature. Tillage does indeed tend to warm the soil up in the spring by reducing the moisture content, reducing the heat capacity of that soil. And we saw, as a lot of other studies have shown, really at all 3 sites, those tillage operations tended to increase that mean temperature in June after seeding around 1 to 2 degrees centigrade. So it does tend to warm that soil up. We also looked at carbon dioxide production in the 2 weeks after seeding as an indication of the effect on microbial activity, microbial respiration, and decomposition rates. And here we did see, as expected, at all 3 sites, those tillage operations tend to be a little bit variable there depending on what the operation was. But the tillage did tend to increase the soil CO2 production, increasing the microbial activity, respiration, and the decomposition from the tillage operations. As one would expect from a tillage operation, incorporating that residue into the soil, increasing the contact with the microbial population, and also breaking down those soil aggregates and exposing the organic matter in them to that microbial activity or decomposition. We also look at the supply rates, the release rates of available nutrients over the 2 weeks after the seeding using the PRS, Plant Root Simulator probes, as a dynamic measure of nutrient supply and release. And we did see some differences there. Not much difference at the Central Butte site, but not surprisingly at the Rostern and the Tisdale sites, where we had incorporated a lot of straw in the soil through those tillage operations. There was lower nitrate supply rates there in those tillage operations compared to the no-till control, as we can see there. And it could also be as well due to the drying of the soil from the tillage operation as well, which will also reduce microbial activity and movement of nitrate in the soil. So finally, in this study, to wrap this up, well, what do we see in yields at the 3 sites? And as you can see there at the Central Butte site, there really wasn't a lot of difference in the yield, really no statistically significant difference as a result of those tillage operations. Interestingly, at the Rostern site, there was a bit of a trend for the tillage to produce a little bit higher yield there, grain yield, compared to the control. Maybe that had to do with some late season mineralization that came about as a result of that tillage operation. At the Tisdale site, we did see a reduction in the grain yield of the following crop, and that was consistent with the reduced nitrogen uptake, the reduced soil nitrogen supply from that immobilization, when all of that straw with its high carbon to nitrogen ratio was worked into the soil. So conclusions from Chris's study there from a single tillage cycle. Overall, the effects in the soil properties were not large or not huge, oftentimes not statistically significant. We could see that trend towards enhanced decomposition, decreased organic matter, some short-term effects on mineralization and mobilization processes, reduced stratification of phosphorus and pH in the layers in that surface soil that I think are an important consideration, and especially with that trend towards enhanced decomposition, what we might expect to see down the road after several years of that. I guess, where does this fit in terms of a field scale? This is a small plot study that we're talking about. You maybe look at this on a field scale, a one-time operation to address an issue, maybe applying it to specific areas where the problem exists. I think you would want to avoid the whole field and repeated operations, because based on what we saw, although that single cycle really didn't have a big impact in most cases on those properties that we are related to soil quality or soil health, like the organic matter content, if erosion comes into the picture, along with accelerated organic matter and residue decomposition. Indeed, over a number of years, we're probably, I think, going to start to see some deleterious effects. And certainly, this one cycle of tillage didn't appear to destroy all that was improved by several years of no-till in those soils, but continued on, especially high-intensity tillage. I think we would expect that to further decrease the organic matter, the surface residue cover, and maybe potentially lead to some erosional issues and additional soil degradation that really doesn't get reflected in a small plot study. Bringing in a little bit more on shallow tillage, just one slide on this from work that was done by Raul Avila in his master's research work more recently, comparing one tandem disc operation versus a vertical till operation on a flax field. And the tandem disc here with discs as shown on the top here. The vertical till unit that was used in this had discs, and it also had rolling baskets behind. And the measurements that were made, shown here, aggregate size, there was a trend towards decreased aggregate size with the more intensive vertical till, but it really wasn't statistically significant. The hydraulic conductivity, which is a measure of the infiltration rate, the rate at which water enters into the soil, little bit lower, but it wasn't statistically significant. The air permeability we measured was also reduced, lower in the vertical till, but again, it was not significant at the 5%, but it was significant at the 10%. So comparing a tandem disc operation to the vertical till, which had the disc plus the rolling baskets, we are seeing a slight decrease in the soil permeability with the vertical till unit, an increase in the proportion of the fine pores. And really, I think that could be attributed to some of the additional packing that takes place by those rolling baskets. That creates a nice, firm, fine, a moist seed bed, but also tends to reduce the permeability somewhat. So folks, that's shallow tillage. The remainder of my presentation, really, I want to talk a little bit about deeper tillage, and specifically deeper tillage to address compacted soil layers. So instead of dealing with the top 0 to 10 or 0 to 15 centimeters, we're going a little bit deeper. Down to 30 centimeters, 45 centimeters, and addressing some soil compaction associated with various factors or processes. And I guess when we think about soil compaction as a bit of a background, what we're talking about is we're talking about the deformation, the breakdown of soil aggregates, the reduction in porosity that occurs under load. And probably the load that we're maybe most familiar with would be load that would be coming from traffic through the field, tire traffic. But in some cases, we can also get compaction from animals, hooves from around a watering site. The effects of compaction, no surprises. We were talking about bulk density right at the beginning. When we get compaction, we reduce those pore spaces. We reduce, in particular, the macropores. We increase the density and strength of the soil. And of course, one of the things that does is it can impede root growth. And one picture I always like to show out of the introductory soil textbook with beans is the impact of that compacted layer, reducing the ability of the roots of that bean plant to explore that soil volume. And different crops have different, and plants have different abilities to push through that hardened soil. But generally, if you think about bulk density, anytime you get above about 1.6, 1.7 grams of soil per cubic centimeter of soil as your bulk density, when you get above that, you're really talking about a lot of plants having a little bit of a tough time getting their roots to penetrate through soil of that density. And similarly, penetration resistance values above, if you're using a penetrometer, penetration resistance values above about 2,000 kilopascals are going to be posing a challenge for the penetration of roots by a lot of different crops out there. There are some pretty good ones. Some of the grasses can do a pretty good job of penetrating. There's another one called the I think it's the root to turnip. Radish. I can't remember the name of it but there are some of some brassicas as well that can do a pretty good job of getting through that compacted, very dense, high strength soil. So we think about compacted soil with reduced porosity. That's also going to have a negative impact on water infiltration, air infiltration, increasing potential for surface puddling. Instead of going in, it may tend to run off, poor aeration. So the result of that also as well is reduced water and nutrient use efficiency by the crop. So we think about tillage and soil compaction, and we recognize that repeated plowing at the same depth can actually create a layer of compacted soil, what's sometimes called a plow pan. And you could actually find this in the old summer fallow days at about the depth where you were going every year with that chisel plow. Right below it, you could find a sort of a plow pan where there was a little compacted layer, higher bulk density, greater soil strength. We also recognize that tillage implements can be used to break through and loosen that compacted layer of soil. And that's a process that we call or refer to as subsoiling. And so I'd like to talk a little bit about the research work that we've done with subsoiling over the years, and go back a few years, about 15 years, back to a study that we did in the Lake Diefenbaker area around Bursay on irrigated soils, and looked at the effect of subsoiling on bulk density, water infiltration, and yield. Why irrigated soils? Well, we thought those were the soils that would probably have the greatest susceptibility to compaction because they're irrigated, so they're wet, and wet soils tend to compact more. And also maybe a little bit more wheel traffic on those fields, higher yields on there, and more things like carts and trucks moving across. So that was where we did our research work. And Brett Ewan was the graduate student who worked on this project with myself, Mike Grievers, and also Garth Weiderman from the Ministry of Agriculture at Outlook. And the unit we used was this paraplow unit here, which, as you can see, is based on shanks here with a narrow profile that actually create relatively little disturbance at the surface. But at the bottom of the shank, we have a kind of a plowshare that creates a lifting action, but relatively little soil disturbance at the surface, not too bad. This is very different than deep ripping. Deep ripping is often referred to, and deep ripping is really refers to the process where the soil is actually almost kind of turned over, and soil from depth is brought up, and there's a fair bit of disturbance. In this case, with the subsoiling, this would be a relatively minimal disturbance type of operation, with the main effect being a lifting at the depth at which those shares operate. And so what we wanted to determine if subsoiling with this paraplow unit was effective in reducing density, increasing water infiltration, and we also took a look at the yield responses as well. So this work was done in the Lake Diefenbaker Irrigation District around Bursay. We had actually at the beginning 3 soil types. We had a Solonetzik, which already started out with a hard pan compacted layer of high density, and a Chernozem, and of a loamy texture, and also a very high clay content vertisol. And when we did this work, it was really wet years in 2010, 2011. We actually lost the Solonetzik site to flooding. So unfortunately, then we went from 3 soil types to 2 soil types. And that's what I'll be referring to here in my presentation results. In this implement, we set it up with 3 configurations, a normal configuration with a 45 centimeter working depth and a row spacing of 45 centimeters. We also were interested in what happened if we pulled it out of the ground a little bit, a 30 centimeter working depth versus a 45 centimeter, so we call that shallow. And then also a wide row spacing where we lifted every second opener up out of the unit. So our working depth was 45 centimeters, but now our row spacing was 90 instead of 45. And we're interested in a wide one because what would happen then if we went wider? That would reduce the draft requirement, the horsepower required to pull it, and what was the impact of that on the soil properties and the yield. So the first thing I'll talk about is the penetration resistance or soil strength. This was measured in mid-May. Following, we had treatments of a fall paraplow operation in the fall preceding and a paraplow operation in the spring, just before seeding. And we measured in the middle end of May. And what you can see here really quite clearly on both the clay vertisol and the loamy textured Chernozem compared to the control, the paraplowing was very effective in reducing the soil strength all the way down to the depth of operation, about 45, 50 centimeters in both those soils. So it was reducing the soil strength, and it was, not surprisingly, reducing the density of that soil as well, especially at the surface, but proceeding again all the way down to about the depth of operation, about 40, 45 centimeters compared to our control, which is the black line. Our shallow operation didn't do as good a job as our deeper operation. That was the Chernozem site. When we measured this again in the fall at the heavy clay site, and this was a really wet season, actually you can see there those differences in bulk density that we saw in the spring actually had largely disappeared by the fall in that heavy clay site. And it was really wet, heavy clay. It seemed like under those conditions, the effect of that operation really didn't last. We measured air and water impermeability, that is infiltration, measuring water infiltration, in this case using a big tray or pan that was set up across the seed bed, both the seeding rows and the covering at least a couple of the channels there that we created with our subsoiling unit. So we measured water infiltration, and then we also measured there in the back of the truck, you can see hooked up air permeability as well, the entry of air into the soil as affected by the subsoiling operations. And what we found for water infiltration rate into the soil, and take you through this on the Chernozem first. We've got over here our control without any subsoiling. And we can see here how the normal configuration applied in the fall and the normal configuration applied in the spring significantly increased the rate of water infiltration into the soil. No surprises there, consistent with the reduction in bulk density and the increase in porosity. Our other setups, a wide row spacing or a shallow application or shallow treatment application depth, didn't work as well. Very evident on the Chernozem. On the Vertisol, what we see compared to the control, interesting. The fall operations, again, probably because they didn't last into the spring, and when we were making our measurements compared to the spring application of those paraplow treatments, fall didn't seem to work as well on that heavy clay soil compared to the spring. Again, we got our best infiltration on our normal configuration. And finally, summarizing this study in terms of the grain yield differences that we saw over the 3 years of the study on that Chernozem and the Vertisol, overall, on average, about maybe 5% yield increase over the unsubsoiled control over those 3 years. So not a huge yield increase. And, you know, some years, like in that Vertisol in particular, we didn't really see any grain yield benefit. So when we put some economics to this and calculated that, first off, the cost of the subsoiling with the paraplow, and these are 2012 costs that we're applying here. So $30 per acre, that included the ownership and the operating costs. Certainly that's going to be more than that about 12 years later today. But $30 an acre is what it worked out to then. And if you're looking at a yield increase of maybe 5% in that first year, and maybe that works about 2 bushels per acre, assign a cost to that, $12, $14, $15 a bushel if you're talking about canola, it's about break even. And so really what that means, and the conclusion was, you need to have some larger benefits or benefits that are going to persist longer than 1 year to provide a significant positive economic return. And unfortunately, this study, we really weren't able to follow it up beyond one year. But we realized there were some things that we needed to look at that were probably going to be important to take a closer look at the economics of this and see refine, how we applied our subsoiling. But from this first study, certainly that subsoiling was effective in reducing the density, reducing the soil strength, increasing water and air infiltration. Persistence of effects reduced under high clay content soils under wet conditions. Didn't seem to last even much more than a year. A limited effect on crop yield at the sites in this study, but I also have to say as well that really those sites, we set our plots up kind of in the middle of the field, away from any kind of wheeled traffic area. And when you looked at the penetrometer resistance values, they really weren't above the threshold value to begin with. So it leads to the question, what could be potential benefits of this subsoiling then under drier conditions, and looking at soils with a more pronounced compacted layer, maybe in specific areas of a field. So this led to our second study, that we did looked at precision subsoiling to address localized compaction. And this was done, a master's project by Raul Avila with myself and Bing C, Tom King, and Mike Grievers. And this is published as well in a journal article if anybody's interested in the details of this, as well as Raul's thesis. But recognizing that there are areas within fields, haul roads, for example, load and unload areas, that there's been more wheel traffic over time, and those are the areas that are probably going to be have the greatest degree of compaction, increase in density, and would be expected to be most responsive to the application of some type of a tillage or subsoiling. And so this study we did actually was done on fields located near my farm. And this enabled us to bring in one of these solonetzic soils, which, because of a high content of sodium and also low organic matter as well at this location, really produced soils that right at the outset didn't have particularly good structure to begin with. And so we wanted to look at the effect of compaction by wheel traffic on these soils and what the impact on subsoiling was, as well as on a regular Turnazem soil of the Haverhill Association. So the tillage operation, in this case, what we used was a John Deere 2100 minimum till subsoiler, kind of like that paraplow unit. It had shanks with a very narrow profile, so not a lot of disturbance at the surface. And at the bottom there was a foot that created a kind of lifting action. Spaced 76 centimeters apart and set to penetrate about a foot into the soil. And so this is what we used, and it was kind of more of a field scale type of study, but we had replicated plots that in the end took up the majority of an 80-acre field. And as you can see there, at that last photo there at the bottom left-hand side, that narrow subsoiler shank really creates a relatively little disturbance at the surface. So leaves a pretty good seed bed behind for the crop. And this is in a solonetzic area of one of the fields here in the solonetzic field. And there you can see that lifting action of that foot at the bottom producing that type of seed bed left behind. Not too bad, but I'm still, I think, probably explains why we saw where you subsoiled where you didn't need it in a non-compacted area, there was a trend towards a slightly lower yield. So the treatments that we had then were a non-compacted kind of a non-compacted control area versus areas that were affected by both long-term and short-term wheel traffic compaction. The short-term wheel traffic compaction we created by running a 3-ton truck loaded with grain through the same pathway or travel area 3 times. And the long-term compaction was a long-term 20-year haul road within the fields. And we looked at the effect without and with subsoiling on soil properties and ultimately the crop yield. And just to summarize this, and on the solonetzic soil, and these were the canola yields that we got. First off, on the right-hand side where there was no compaction on the solonetzic soil, areas where there was no wheel traffic, either short-term or long-term, this was the yield without any subsoiling. And when we applied the subsoiling, no statistically significant difference, but again, maybe a trend to slightly lower yield because of just maybe, and this was with canola, the seed bed wasn't as good as when we didn't do the subsoiling at all. Moving over to where we had long-term compaction by wheel traffic, and there was no subsoiling done on it. If we compare that to the yield where there was no compaction, we see significantly lower yield here as a result of that long-term wheel traffic compaction. And when we look at the impact of the subsoiling on that, we see a significant large increase in yield in that area that was experienced long-term compaction by wheel traffic. So compaction by the wheel traffic long-term significantly reduced yield in that solonetzik soil, and where we subsoil it, increased the canola yield rather substantially. And so we did the economics on that, applied to that specific area, a net gain of $165 an acre. Now, if we move on to the Chernozemic soil, which better structure to begin with, and we look at the effect of short-term compaction, we've got all our treatments laid out there on the bottom, and I'm not going to go through those in a lot of detail. That's the total biomass. There's the grain yield. Really, it's pretty much a flat line. There's no difference in any of those treatments in terms of the grain yield. Following that short-term compaction. And that probably reflects the fact that those freeze-thaw cycles that we experience in the winter, the fall, the early spring there in that Chernozemic soil probably got rid of a lot of that compaction. And overall, it was short-term and really was not as severe as what we saw in that long-term repeated 20 years of haul road out in that field. And so if you're not getting any yield increase from the operation, it costs you money to do it. We calculated out a negative economic return from that subsoiling operation. So I think the conclusions that came from our work, is that severe compaction issues are probably not widespread across most prairie fields out there. And I think it's important to get out there and do some testing with a penetrometer to reveal those areas that exist within that field. The kinds of places that you'd want to look would be soils that are poorly structured to begin with, like those solonetzik soils, and areas really in any field, and particularly those fields that have experienced long-term traffic compaction, like wheel tracks, traffic roads, load and unload areas that you might find at the entrances of fields. And I think here, using a precision approach where that subsoiling is applied to only those identified problem areas where you're exceeding that threshold, from our work, really would seem to be an effective means to improve the yield and maximize the economic returns from the operation, as opposed to going out and doing the whole field, and maybe a large proportion of that field really didn't need or didn't have the ability to respond to that subsoiling operation to begin with. And so with that, I will end my presentation, and I'd like to acknowledge all the funding agencies that have contributed to this tillage research work over the years, and the folks who have supplied us with equipment for some of our trials. And thank you very much. So I'll end off there and turn it back to you, Jeff.
Thank you for the great presentation, Jeff. As a reminder, if you have any question today, please enter them into the chat box at the top of your control panel. I will now give everyone about 2 minutes to get their CCA credit, which I will put the QR code up on the screen here. If you have any question or are going on restroom breaks, we will start with the question period in about 2 minutes. So I will start with the first question. What is the impact of tillage on the wet soils in different soil zones? And does pH of the soil type have an impact on the compaction?
Okay, so I guess, and the question was, does the pH have an impact on soil compaction? Yeah. And I would say not directly, but the pH can give you an idea of the chemical composition of the soil, which may be related to the susceptibility of that soil to compaction. And so if I see a soil with a high pH, that high pH may be indicative or reflecting a high sodium content in that soil and poor structure to begin with. And so, especially if that pH was, 8 or above, and you do your composition of exchangeable cations, you got a high proportion or percentage of sodium on the exchange complex, that would say that's a poorly structured soil, probably because of the sodium causing dispersion, and might be more susceptible to compaction than other soils where you don't have as high a content of sodium. Acid soils, getting down in the low pH side of things, below 7, I wouldn't say that those acid soils would be particularly any more susceptible to compaction than soils with a pH closer to neutrality. But if that acidity is maybe having a negative effect on the crop production and the organic matter additions to the soil, that anytime you have lower organic matter content of the soil, that's also going to increase probably the susceptibility of that soil to structural deterioration by things like smearing and also compaction as well.
Okay. Then there's another question about there seemed to be a trend in the being concerned about tillage interrupts mycorrhizal hyphae and microbe habitat. Is this disturbance something to be concerned about?
Yeah, that's a good question, and I think it has been shown. I think that in some cases, and I remember some work I think that was done at Indian Head a few years ago that showed that the tillage does tend to decrease the mycorrhizal hyphal networks in the soil. I've never investigated this personally in my own research program, recognizing that many crops are mycorrhizal apart from the brassicae, and so I do tend to believe that those crops, once they're seeded in and grow, are able to reestablish those mycorrhizal networks relatively effectively, even if there was a preceding tillage operation. But I'm not sure how long those mycorrhizal hyphal networks might persist with or without tillage in the system over time. So yeah, it's a good question. I don't have an answer for it.
Okay. Yeah. So the next one we have is could repeated subsoiling negatively affect soil aggregate stability?
Yeah, that's a good yes, and I guess repeated subsoiling. And we're talking about a deep tillage here, because of the relatively little disturbance that occurs at the surface of the soil with the narrow shank profile of the implements that we used in our study, I don't think you'd see a major impact on the aggregate stability. There's some disturbance, and any kind of disturbance or breakdown of the aggregates will tend to also decrease the decomposition rate. But most of what the subsoiling is doing is it's doing that lifting action at depth. And I don't think that's going to have a big impact on aggregate stability compared to, let's say, a tillage operation, a high-speed tillage operation that was done repeatedly at the surface of the soil. I think that probably would have more of a negative effect on aggregate stability in terms of repeated application than the subsoiling.
Okay, so we got another one. Would you expect to see a benefit to subsoil in saline area around sloughs to reduce salinity or improve water movement?
Yeah, and that's a really good question too. And we looked at this a little bit, and it seemed like in the soils, we did a little bit of work with some soils that had some salinity. It wasn't right at the surface. It was salinity in the 30 to 60 centimeter depth down deeper. And it seemed maybe like by increasing the porosity and increasing the water infiltration, we were able to move the salt a little bit deeper down in those soils. But recognize that if the salinity is close to the surface and is close there because the water table's there, going in and doing that subsoiling is likely to have little or no effect on the salinity of that soil. And in fact, sometimes opening that soil up through some type of a tillage operation and increasing evaporative losses from the surface, increasing capillary movement of water to the surface might actually make that salinity problem worse. So I guess in a short answer, I would say subsoiling is not really the answer to a salinity issue in the majority of the cases out there. It's a high water table, it's a water issue, and you got to do something to try to bring that water down, like growing a forage on there and lower that water table.
Okay, there's another question I see there. Would there be any advantage to shallow tillage in the fall to break capillary rise and preserve moisture?
Yeah, and that's kind of like that concept of the dust mulching in an extreme sense, or tillage operation to seal up the cracks. And it might have some benefit on that if you're dealing with a soil that has a lot of cracking in the fall to begin with. And I'll go back to the old days in the old tillage fallow days in the 1970s that I remember, and going out and what was called pre-working, which was tilling all your fields early on in the spring to seal up the cracks that were left there from the winter and that have been now that snow is gone and the cracks are opening up as the soil dried, to basically seal that surface off. The fall, I'm not sure. I think I would avoid that in the fall, because the other thing that you're doing in a fall tillage is you're also burying some residue. You're getting rid of your standing stubble that helps to trap the snow. So if anything, any kind of like a strategic tillage that might be done to seal up the cracks, I think would probably be most appropriately done in the spring of the year.
Okay. The next one I'll go is, do you think there could be a benefit to subsoiling on the crops with more shallow root system like pulses?
Yeah, and that's interesting. And we did do the subsoiling in those studies that we did that I talked about with the subsoiling. We had crops in rotation. So we had a wheat crop, we had peas, and we had canola. It almost seemed like, for whatever reason, the canola seemed to benefit more from the subsoiling than the other two crops did. And maybe that was a consequence of just the canola roots, perhaps, and the environmental conditions were going down deeper, and in general, and that lifting or loosening that extended through the profile really allowed that increased root development and exploration for that crop that year. That being said, I mean, shallow rooted crops like pulses, and as you can see, as I showed in those graphs, the effect of that subsoiling on decreasing the density, decreasing the soil strength, really extended from the surface down to about 40 centimeters. So that's a fairly shallow depth. And that's where those more shallow rooted crops like the peas, for example, and some of our other work is showing this as well, that's where the roots tend to proliferate. So I also expect to see, and maybe even more so under certain conditions, especially, maybe low fertility conditions, that the pulse crop might, particularly the shallow rooted crop, might benefit more from that subsoiling operation.
Is there a risk of solonesic soil of problems occurring when the BNT is broken up, allowing sodium-rich groundwater under positive pressure coming to the ground surface layer?
Yeah, and I guess I go back to on that solonesic soil. I remember some of the old deep ripping work that was done, and when you brought that BNT horizon up to the surface, you had big hard lumps and chunks of clay, and it was a pretty ratty, rough seed bed for any kind of crop, really. In terms of it increasing the salt migration to the surface, oftentimes what we find in those solonesic soils, and I'm thinking right where I am along the Missouri Coteau there, they are saline and solonesic. So you've got a hard B horizon, and right below that, you've got salts. And I think under those circumstances, especially if that's close to the surface, indeed, Opening up that soil, you're increasing the potential for more capillary rise to the surface, even a potential impact more of that artesian positive pressure that exists there, and having more salt migration move to the surface. So I'd be wary of doing any kind of subsoiling where you've got that BNT horizon really close to where that layer of salts exists in the soil profile.
Okay. Our next question we have, can you expand on subsoiling on a sandy soil versus a clay soil?
Yeah, I guess, and we never did. None of our trials were conducted on really sandy soil. We had loam, we had clay soils, we had clay loam. Um, Normally, in a sandy soil, a really sandy soil, I wouldn't expect to see as much compaction issue to begin with. Some of the worst soils are the soils of higher clay content, low organic matter, and if they're wet. That's where you really end up with the greatest potential for compaction typically. And of course, associated with a greater load or downward pressure. And so I would say a really sandy soil, I would guess that it would not be as responsive to subsoiling. I would also say that a really sandy soil, you probably wouldn't see as many issues with the compaction arising to begin with compared to a soil of heavy texture, clay soil, especially on wet soils.
Okay. So the next question we have, do you think that the heavy harrow may create the same surface compaction as vertical tillers?
That's a good question. It's one I've wondered about as well. And there's a lot of down pressure you can create with that when you run those harrows at a steep angle, and you've got them laying right down, and I think there's the potential to create that. I don't know whether it would be a very thick layer that would be compacted. And I guess I'm thinking you'd probably have to keep doing it repeatedly in order to produce something that's measurable. But that's an interesting question. I think the potential is there. I don't know whether anybody's measured that before or not, but would be something interesting to take a look at. You'd really need to be looking at sampling that soil in very narrow or small depth increments. But that's a good question, good thought.
Okay. Any idea on how long the effect will last on solonistic soils?
Yeah. I think you should be able to get, if you did it when it was dry, I think you probably should be able to get a couple years at least out of it. But I go back to that really heavy textured clay soil in that first study there, and man, it was really wet. That was the year with about 15 or 16 inches of growing season precipitation, which is really, really not typical. And it was an irrigated field too, and it was gone, after that first year. Solonesic soils typically, they're not really heavy clay. You've got that BNT horizon. It seems like overall the subsoiling creates more lasting effects when it's dry. And you're doing the operation when it's dry and when it's dry as opposed to wet. But yeah, I would think you should be able to get two years out of it. And I wish we would have been able to keep that trial going for longer than what we did, to really look at the long-term effects of that process.
Okay. Next question we have, can you further explain the fact that shallow tillage could have more moisture retention with the dust layer on the top, but at the same time also have less nutrient availability in the drier soils?
Sorry, can you repeat that again?
Yeah. Can you further explain the fact that the shallow tillage could have more moisture retention with the dust layer on the top, but at the same time also have less nutrient availability in the drier soils?
Yeah, so I guess when you think about the tillage and what it would do in drying out the soil, and also breaking down the aggregates and creating this very fine layer of soil on the surface that's dry. It prevents any kind of, reduces any kind of further rise by capillary action. The capillary areas in the soil, they're no longer connected, so you're not getting that capillary rise. So it helps reduce evaporation from depth, also by sealing up those cracks. But the dry soil, from a nutrient availability standpoint, is going to impede nutrient movement in the soil by processes like diffusion and mass flow. So within that dry area, and it may be dry enough, you're also not going to get germination. You're also not going to have very good nutrient availability, because in part because that soil is dry and the nutrient can't move. I'm not sure whether I really answered that answered that question very well, but yeah. So I mean, and I also think particularly, and I remember back, sealing up those cracks that you get in higher textured soils, low organic matter soils at the surface that act as conduits for moisture evaporation to occur, and then producing that kind of layer, that almost like a dust mulch, that dry soil on the surface, then that really covers and fills everything in, helps retain moisture, from the sense that it stops you from, or reduces the amount of moisture that's being lost from depth. But there's a lot of negatives that are associated with that in terms of erodibility, and even, I think, as the question's alluding to, not only just the germination of the crop, but also the ability of the roots to move to it.
Okay. Next question.
I'm sorry, ability of the nutrients to move to the roots. Yeah.
Okay, the next question we got is, in terms of nutrient stratification, would it be considered a good idea to add in a tillage pass to promote mixing?
Yeah, and this is something I've thought about for a long time. And I go back, we really didn't, although we got rid of the stratification or reduced it, it didn't really impact what we saw in terms of uptake of phosphorus by the crop, which says to me that, although you got rid of it, it really didn't affect it, the availability of that phosphorus, very much. It really didn't improve it particularly. And I guess maybe to think of a no-till soil, you've got good moisture right to the surface. For most crops, you've got roots where that phosphorus is. If you're putting it down in the soil with the seed at the depth of seeding. Interesting too. That was done, like I said, 15, 20 years ago. Would be interesting to look at it now again. I don't think I would go out and till a soil just for the purposes of reducing the stratification, unless it was extreme. And I don't even know what we would call extreme. But like I say, we tilled the soil and tilled it a lot in that max tillage operation, and it really didn't seem to have any significant effect on the phosphorus uptake by the plant, which reflects the phosphorus availability in the soil.
Okay. So the next question we got, are you able to comment on the subsoiling areas of the field with high disease pressure?
Yeah, that's another good question. We didn't do any disease assessments directly. It would be good to do that now, I think, especially since that work was done. A lot more issues have shown up with the root diseases, particularly of the pulse crops. I tend to think that if you can improve the drainage and not have that saturated layer in a solonetzic soil existing after a rainfall, by reducing the density and increasing the porosity, increasing the infiltration and the drainage, the movement of water, I think that would have a positive effect on reducing aphanomyces in peas, because aphanomyces is the disease that requires basically saturated soil conditions for those oospores to be able to move around in. And if you can get rid of that, I think that improvement of the infiltration, the drainage, saturated soil conditions experienced for a long period of time in those solonetzic soils, there could be a benefit there. We didn't look at it. I don't know whether anybody else has, but it would be, I think, another interesting avenue to pursue. But my expectations, if you can reduce standing water in a field, if you can reduce saturated layers in the soil, that can be a benefit in reducing diseases, particularly disease like Aphanomyces.
Okay. Next question we got is, what do you see as the opportunity / challenge to use tillage as the means to control weeds?
I think maybe the opportunity is to consider a single shallow tillage operation that might be employed once in a while, and maybe once every couple of years, 3 years, to go in and do that operation that may help to deal with some of those weeds that have developed resistance, multiple resistances to different categories or classes of herbicides, to maybe deal with some of this stratification issue with both pH, phosphorus, some of the other immobile nutrients like potassium. I think maybe a strategy that would be suitable to employ. And that's where I would see it, particularly on the weeds side of things. Also recognizing that, tillage in some cases can promote weed germination, weed seed germination. And sometimes maybe that's desirable to produce a flush of weeds that you might go in and address again with a herbicide, or even with a second tillage operation if need be. So I think it's another tool in the toolkit, again, applied judiciously, and really aiming towards minimizing the amount of residue elimination on the surface that helps protect that soil against erosion, minimizing the kind of breakdown of aggregates in the soil that promote decomposition and loss of organic matter, and also reduces the susceptibility of the soil to wind and water erosion.
Okay. So that's most of the questions. Thank you again, Jeff, for all that great information. We appreciate the time you took to join us here today.
Great. Well, thank you very much for having me.
Hey, you're welcome. So thank you very much for coming. And I know you had some technical issues, but we figured that out.
Indeed. Okay. That's why we have